Hello, everyone. My name is Paula Popa, and I work at CodeMart as a software developer, most of my work being related to the Virtual Brain project. Today, I am going to talk about our work towards integrating TVB with the EBrains platform. I will start by summarizing which are the packages involved in the TVB ecosystem. Then I will give you a quick overview about the TVB main concepts. And afterwards, I will go into more details about the TVB EBrains integration. So, regarding the TVB packages, I believe this diagram showcases nicely how all these packages work together inside the TVB ecosystem. Mind that these are all public on GitHub. I will start with the red box, which showcases the TVB Core. And TVB Core means a set of multiple packages which are listed here, and I will speak about them on the next slide. They can be used independently from PyPy, or we also pack them all together inside a TVB distribution that we usually public on the website and package in a manner that is compatible with all operating systems. TVB is a large-scale simulator. It works on region level, and its main input is the brain represented as a network of connected regions. Such a network is what we call a connectivity in TVB, and it's part of what we use in a virtualized patient data. Depending on what the user needs to simulate with TVB, it can also contain different data types. We also have surfaces, sensors, different types of mapping between this data, like region mappings that inform TVB which vertices of a surface correspond to a certain region of the connectivity, and so on. So all of this input data that goes to TVB is what we call the virtualized patient data. The TVB output is mostly time series, the central flows of TVB being the simulations, but we could also have other types of output data depending on what the user is doing with it, like different analysis on time series or manipulating connectivities that generate new connectivities, and so on. Now, in realistic use cases, a user will want to work with data that is personalized for a patient. And this is the main focus of this EBrains platform. So the user would start from imaging data for the particular patient he wants to study. And while TVB does not work directly on the imaging data that is represented here, we need to use another tool to transform data held in images towards data that TVB can read. And such a tool is what we call a reconstruction pipeline. So a reconstruction pipeline is capable to take directly the imaging data of the patient, pass them through a series of processing steps that allow it to extract connectomes and different geometries of the brain surface, the region mappings, different atlases, and so on. And as a last step in this pipeline, the focus is to actually take this extracted data and put it into TVB compatible formats. So as a result, from the reconstruction pipeline, we would get files that TVB can directly read. And once the user has these files, he can directly upload them in TVB and do its further analysis with them. Such pipelines we have multiple of implementations for such pipelines. It depends on the user needs on which one fits better his use case. Again, these are also available on GitHub. They are all public. And I think they will also be integrated towards the EBrains platform.
Yeah, actually they are already in part.
They are already, okay.
If you're interested to know more about that, I would advise you to go to the videos from last workshop. There you will find some information about them.
Good. Then we have these other packages. They are here in the middle. One is the TVB Epilepsy and the other is TVB Multiscale. And these ones work together with TVB in order to offer even more complex ways to simulate. For example, the package we call here TVB Multiscale proposes solutions to co-simulate between TVB that works on the region level and an external simulator like NEST in this case that works on a lower level of details. But this will be subject of discussion later today, so you will get more insight on that. This would be the main packages involved in this integration. The focus on my talk will be towards the TVB Core one. And the actual code from TVB Core comes in two major forms. The first one would be this a box that we call TVB Library, which is a lightweight and standalone Python library. Here is where all the scientific code lays. By scientific code, I mean the simulator code, algorithms that can do analysis on time series, and also all the data types that TVB uses. As I mentioned earlier, data types are the concepts of connectivity, surfaces, region mappings, time series, and many others. So you could use that by itself in order to do simulation at a command line level. But we also have this other package, which is called TVB Framework, that is indeed more heavy, but it brings with it also a web GUI for the TVB application and a solution for data storage. It depends on TVB Library, so it comes with all the features that TVB Library proposes, but plugs them into a framework that is capable to display them in a GUI and store all the data in a structured storage. Within the TVB framework, the flows follow these main concepts. We have in TVB users. One user can create multiple projects. Inside each project, a user can launch multiple operations. And by operation, we refer to the action of launching an algorithm. And algorithm in TVB can be one of the following categories. We have uploaders, which are considered algorithms. So the whole code that is able to parse data that comes from different data formats and put it in the format that is common for the whole TVB storage. That's one of the categories of algorithms. The next one would be the analyzers. These are algorithms that work on time series and are able to compute different metrics on them. The simulator is again a type of algorithm here. It works on connectivities and outputs the time series which analyzers can work on. And another category is the visualizers, which again is code that can process data from the TVB storage in a form that can be displayed in a viewer in GUI. So to reiterate, a project has many operations, and when an operation is finished, it outputs data types. So data types are results from operations that were launched within the TVB application. And I mentioned earlier, I will mention again, data types are all of these concepts we use often in TVB, like the connectivity, the surface, the time series, a Fourier spectrum, which is an example of a result from an analyzer algorithm, and many others. I'm mentioning this because I will also mention them further when I will speak about security. So I think it's important to keep in mind that in our storage, data is organized in the following hierarchy. So we have multiple projects. Each project has multiple operations. Each operation can have multiple data types. And now moving forward to the TVB EBrains integration. Before EBrains, TVB was mostly distributed as a standalone application. Users would download a package from the official website and then run it on their local machines, or maybe install it on clusters with few users to access it. EBrains initiative brings us a new challenge in the sense that it requires us to support a centralized installation for TVB. That means that we have to deal with requirements for better authentication and additions of security for the data we use there. As this is ongoing work, I will present here some of the main principles and solutions we are working on, but not a final implementation, since this is still subject to evolving in time, depending on the infrastructure or requirement changes. We are working towards these objectives. We aim to have a scalable and reliable deployment of the TVB Web GUI running on a large infrastructure. We want to have the possibility to distribute jobs on an HPC backend in a secure manner. And of course, we want to ensure that we respect privacy policies and GDPR as we are dealing with data that is considered personal, even if it has gone through all of these pre-processing steps already before landing on the TVB storage. Regarding the architecture we have in mind for the EBrains deployment, I think this figure showcases best the architectural blocks that we envision as necessary for this integration. We have in the center the TVB web, as we need to deploy that somehow in the EBrains infrastructure. This TVB web instance will allow authentication of users through some authentication tools. So we need to allow a large variety of users to access this instance. So we will integrate with an external authentication tool for it. These users will want to upload their own data for simulation and analysis in TVB. But as this data can be sensitive, we need to provide them with some data encryption tools before upload, as Misha has also said before. The data uploaded by users and data that is generated through the TVB operations is stored in the TVB storage, which again should be secured. So we need to provide encryption at the TVB storage level also. And finally, we should support an HPC backend where users could submit heavy jobs. This is a high-level view of the components involved, and I will go through each of them separately. I would start with the black box, which is the TVB web deployment, and I will show you the solution we currently have for that. We analyzed existing alternatives of deployment and found the Openshift environment compatible and easy for us to maintain. Openshift is a container orchestrator installed by the EBrains team on the CSCS infrastructure. We have access granted here as developers. Thus, we can create projects and have a good control on their configurations. we can deploy here and operate Docker images, even if they come from the public Docker hub. We are not constrained to use the internal Docker registry. So what we have done is to create one project for the virtual brain in Openshift. And to configure the deployment in the following manner, we start 2 Docker containers, which are represented here. One of them is the TVB framework called the virtual brain. And the other instance is a Postgres Docker container, which TVB framework uses for DB storage. We can set up some auto-scaling here for pods, and we can choose even the way they should be scaled based. We chose to scale on the CPU usage. So we have a rule that says something like when CPU goes over 80%, it can scale up to 10 replicas for the TVB. But yeah, we consider this only a starting point towards real scalability. We plan to have benchmarks and monitoring of real usage before we can draw a conclusion on how we should scale and yeah, actually configure, actually define a fine-tuned scalable configuration. We plan on analyzing the amount of users accessing the application and the type of operation they will mostly do. So we could decide on scalability based on real information, on how real users use this instance and not just at a hypothetical level. So having this deployment configuration, we are able to deploy the TVB GUI at this public URL. Now, yeah, who can access this? We have integrated the authentication with the HBP Identity and Access Management System, which is based on Keycloak. Thus, any valid account in the HBP Keycloak can immediately log into this TVB web installation. And yeah, we'll have access to the default project, which is publicly shared together with TVB. The main advantage of that is that users could learn how to use TVB based on this default project and experiment with its features. And then, of course, a user could also create his own projects, but at this point, he will be responsible in terms of who has access to that data. Now, going back to this diagram, I have described 2 blocks, the TVB web and the authentication tool we have integrated for it. I will continue now with the security aspect, this being a critical one that we are currently considering for future architectural decisions. And we want encryption to happen at 3 levels during the TVB flows. The first level is at upload time. The data arrives encrypted in TVB through its upload functionalities. This upload is done by data owners that have data access permissions only granted to them. So yeah, they are in control of how and if their data should be shared with other users. This means that they also have the responsibility to do the encryption before putting data into TVB. And we offer a solution that helps at this point by using a pair of public and private keys. We generate a pair of public and private keys in TVB and make the public key available to the users in a common place, together with a guide on how the user should use that particular public key in order to encrypt its own data. Once the data is encrypted, the users can directly upload it through the TVB GUI. Everything will go through HTTPS. And afterwards, on the TVB server, actually only the TVB server will be able to decrypt that data, since it is the only holder of the corresponding private key. Important to mention here would be that the whole code that we use during this upload functionality is done inside a separate process in order to avoid possible malicious access through uploaded scripts that might give an attacker the opportunity to access in-memory data that might be sensitive. And yeah, once the upload is done, the data is moved inside the TVB storage, which yeah, also needs to be encrypted, and will be encrypted with a different method. So even if somehow the private key comes in the hands of an attacker, it won't be able to access the TVB storage in any way. We publish our public key at this link. Anyone could access it from here. And we also publish a notebook with guidelines on how users should do this encryption. And yeah, it's available at this link. Okay, one more thing here, we are also taking into consideration to periodically change the public and private keys used for the upload to mitigate possible attacks and possible attacks consequences, let's say. Limit the data that would be revealed to the attacker in case the private key is stolen. This will also mean that users need to encrypt data only short before they upload it to TVB, because after a while the encryption might not be compatible anymore. They might have used too old public key in order to TVB to be able to decrypt the data anymore. And for this scenario, TVB will provide some meaningful error messages to users in order to inform them on how to proceed and be able to upload the data. Now moving on to the next layer where we need security. And yeah, this is the TVB storage, which holds all the data together. This is a work in progress right now. We are thinking about solutions. And yeah, this is what we call data at rest in TVB. Of course, data at rest should be always encrypted. And decryption should happen only when user needs to do something with that particular data file. We have a first solution in progress. We are currently analyzing the possible enhancements to that. We have to keep in mind at this point that we are dealing with storage that is used on a web application, and we don't want to slow down very much this web GUI in order to keep having a decent user experience there. Yeah, and we are also keeping in mind that we want to come up with a solution that adds minimal changes to the TVB framework API. So the main idea would be to encrypt TVB storage at all time. While it sits on disk, it is encrypted. And the decryption should happen only when the user logs in to the application and selects a project. And in the current situation, we decrypt the whole project. So the next actions the user would do in the TVB web GUI would happen in the same manner as before. No slowdowns. Data is already decrypted and ready to be used in the GUI. When changes happen to the decrypted project, we are doing a synchronization between these two versions of the project, between the decrypted and the encrypted project. And this happens as a separate process, this synchronization. So yeah, the user won't feel it very much. We keep a queue in order to avoid possible synchronization conflicts. And every time we write something in the decrypted project folder, the project is pushed to the queue for a new synchronization to happen, and so on. When does the decrypted data leave the storage? Short answer is when it is not used anymore. And what we mean by that is when the user logs out of the application. Another option would be when the user selects another project. So we will clean up all the decrypted files done on the original project, keep only the encryption version of that, and decrypt the newly selected project for the user. But yeah, this is not so straightforward to say that when the users log out or switch projects, we immediately clean up the data, because we have to keep in mind the synchronization part. So the third meaning of when data is not used anymore is when the synchronization between decrypted and encrypted project is finalized. So even if the user logs out, we still have to wait for the synchronization process to finish, and only afterwards we can clean up the unencrypted files. As I mentioned, this is work in progress. We are still thinking on ways to enhance this. We currently encrypt everything with one key. And yeah, a next step towards better security would be to have multiple keys. So we avoid the situation where an attacker would get our single key and access all the storage. It's always better to have multiple keys. So anyways, if an attacker would get one of them, it doesn't have access to the whole storage, only to a small part of the data. This could happen in many ways. The solution we are thinking of, we might generate a key for each project, or we might generate a key for each user. These are all in discussion right now. And yeah, this is a big challenge for us. And yeah, we are also enthusiastic to find the best solution. And moving forward to the third level of encryption, or let's say the last component of that architectural diagram, which was the TVB with an HPC backend. Here we will also need encryption because we have parts of data which is switching location from the TVB storage towards the HPC site. So we are speaking about these two locations here. The first one in blue is, as before, the Openshift installation of the TVB web, and the yellow one in here is the backend that we use from CSCS. And on short, what we do on the back end of CSCS is that we schedule a job that will run inside a Docker image in order to run a simulation or another heavy operation that the user might have. The steps before actually running that simulation would be to decrypt the data that sits on the HPC node. And yeah, after the simulation, we have to make sure that we encrypt the results before putting them back to the HPC node. By putting them back to the HPC node, I mean out of the Docker container. Encryption, decryption of the data happens only inside the Docker container. Okay, when a job is finished on HPC, we have to notify TVB somehow in order for it to be able to download the results. So this would be in short terms, the story of what we do on the CSCS side. There is a bidirectional communication between these two locations because we need at first to upload the data to the CSCS location. also send it the information about the job we want to schedule. And afterwards, we want the code, the job running on the CSCS to notify us back whenever it is done running, so we can stage out all the results from that simulations. This stage in and stage out communication is done through the UniCore REST API. There we use we currently use our personal accounts, which are HBP key clock accounts linked with our personal CSCS key clock accounts, and that allow us to send jobs towards UniCore directly to the CSCS location. But we want to extend this feature in the sense that we want to allow any user that has an HBP account to be able to send its high demanding operations towards the HPC backend. So we are currently working towards a solution for that. And we will use a service account that the CSCS key clock will make available for us. And I will go in the details of that a bit later. What I would also enhance here, maybe let's go to this diagram. Even if it seems complex, I think it showcases a bit better the steps we do for this integration to happen, for the TVB and the HPC backend to happen. Let's say the user wants to start a simulation, a large simulation, and what we do is, okay, at first we authenticate a user, and then we gather all the files that this simulation will need to access. We encrypt them. Important here would be that we generate a key for each set of files that we are sending towards the CSCS node. We upload the encrypted input files via the UniCore REST API together with a script that will schedule our job there. So all of this happens through HTTPS, and our input data ends up in the Scratch folder on the CSCS node. And then the script to schedule our job is started. And whenever the job starts, we start a Docker container. On the CSCS side, they use Sarus instead of Docker, but it's capable of running Docker containers. Then we mount our folder with encrypted files inside that container, and we start our simulation code. The first step is to decrypt the files, and in order to do that, we will need a key. So the password that was used to encrypt them. We don't send the password together with the encrypted inputs on the network, as Misha also highlighted in the previous presentation. It's better to keep them separate at all times. So in order to us in order for us to be able to decrypt the files, we first do an authenticated REST call towards the TVB web. It offers also a TVB REST API that we could call in order to ask for the particular password used to encrypt these files. Then we decrypt them, and then our simulation process can begin and generate output files. When this simulation is done, we encrypt the files, and then again through an authenticated REST call, we notify the TVB instance that the job is finished. And yeah, we mount back to the CSCS node only the encrypted file. So any decryption on the CSCS side will happen only inside the Docker container, not outside of it. So now we are at the state where TVB is waiting for an operation to be finished on the CSCS node, and we have the data, the results prepared there. We have also notified TVB that our job has finished. So we move on with downloading the encrypted output files again via Unicore. So we do the stage out step here. We bring all the encrypted files back to the TVB site and yeah, decrypt them in order to update our storage with them and our DB. And then again, the storage will be kept encrypted for later. Again, this is a totally different procedure of encrypting data than what we do for the other two layers. And most importantly, is a totally different procedure than what we will do for the TVB storage. So any password that could get on an attacker's hands won't be possible to be used in order to decrypt the TVB storage or any other operation that was launched on the CSCS node. So one password can decrypt only one operation that was launched on the CSCS node. Here, some communication steps are also critical in the sense that TVB web might be down before being able to retrieve the results. Yeah, and we need to find out what are all these failover scenarios. To start on that, we have added a separate process that would start when TVB web starts and check the scratch folder for any operations that are still in that TVB still considers pending or running and doesn't know if they have been finished either with success or with failure. So for all the jobs that are still pending, we check again the scratch folder and stage out any results that there might be in order to update our TVB storage with them. Okay, as I said, this communication currently works with our personal accounts, with which yeah, are linked between the HBP key clock and the CSCS key clock. We have a service account on the CSCS key clock for the TVB application, and We are working together with the CSCS group and other people that are involved in this in order to find the proper solution to use that service account with any HVP user that might want to launch jobs there. Yeah, but this also brings another set of challenges. And by that, I mean the fact that when talking about having a TVB service account for CSCS and exposing this to larger access, we will need to monitor and ensure that the user actually use that in the proper manner. And yeah, again, as a first step towards doing that, what we have come with is a way of monitoring user actions. And what we do is we keep this separate log file where the only information about a user is its identification key that comes directly from KeyClock. So yeah, if there is a need to find out who did something with a specific set of data, we can use this ID in order to tell the KeyClock server administrators which of the users we are looking for. In terms of what we log, we currently only log the actions done by the users within the GUI. So, for example, this is a list of logs that are stored here during a simulation configuration. So as you can see, a user sets a connectivity he wants to use for simulation, and the connectivity he uses has this particular ID. Then he chooses some coupling parameters. Yeah, then he chooses a surface and so on. So together with the TVB storage, we might have a way to determine which data set is used by which user for what purpose, but we cannot do that only having the log file for now. So yeah, if that is a requirement, we will have to work a bit more towards that. Of course, we will have we will make sure that the users are informed about this, about the fact that we monitor their actions at in a certain manner. And we will make sure that the privacy policies and the GDPR is respected. This includes also limiting access to these logs in terms of who can access them and what reason they would have to do it. Okay. Moving forward, I will also like to point out some of the TVB plans. There are many, but in a few words, yeah, the most important right now is improved security. We still have to work on our solutions and find out the one that fits best the requirements and yeah, our own code. Then the idea of optimizing the usage of HPC resources, because now we have a flow that lets users launch any simulation there, but it would be nice to come out with a solution that fills up the entire node. Maybe we could wait for multiple operations to be configured before submitting them on the HPC side, and then yeah, submit all of them in a batch so they can be run on the same node. These yeah, are still in discussion and yeah, for future work. Then there is also the fact that we should track the CPU quota for each user. And regarding the deployment that we have on Openshift, we have to calibrate our parameters and scale based on real usage needs. Where we are now, the current releases are the following. So for the TVB distribution, as I said in the beginning of my talk, the TVB distribution contains all of the packages involved in the TVB Core and is built for each of the operating systems. So yeah, one could easily take that and install it locally and have the whole TVB ready to run. We are still at version 1.5.8 there. This means that TVB distribution is still Python 2. And we are working towards moving that to Python 3. And regarding Python 3, what we have in that direction are packages on PyPy for each of the components of TVB. So those 4 components that I showed in the beginning of the talk, the TVB data, the TVB geodesic distance, the TVB library, and the TVB framework. We are at version 2.0.8. We have a release this week towards 2.0.9. Will be soon available and will also be updated on Openshift. Regarding Docker Hub, we also have Docker images compatible with the latest released versions. On GitHub, we have the TVB root repository, which holds all the TVB core packages. And yeah, here we are working towards version 2.0.9. Regarding the version of the TVB web with security included, with the HPC backend included, and yeah, the REST API, that is currently, let's say, an alpha version on EBrains, because we have a version deployed there, but on the development platform, not on the production one. I don't think I mentioned this. Openshift offers 2 platforms, one for the production applications and one for the ones that are still in development. So yes, we have a deployment on the development Openshift site, but is there for us to test our solutions and ensure that they fit into this infrastructure. Okay, and of course the plan before the end of the year is to have a release 2.1 for the whole TVB distribution, and yeah, have all the PyPy packages in the stable form. So that those being said, I would like to thank you a lot for attending this talk. I hope you found it useful, and yeah, have a nice day.